SwayamPrabha. Digital India. Educated India.
Good morning. Today I'll solve some problem on axial flow compressor. Let me state the problem number 1. The first stage of an axial compressor has the following data at the mean radius. The stagnation temperature rise is 22 K, mass flow of air 25 kg per second, degree of reaction is 50%, rotational speed 150 revolutions per second, axial velocity through the stage 157 meter per second, work done factor 0.95, blade speed 200 meter per second, pitch to cut ratio 0.8, blade chord is 37 millimeter. The ambient conditions has given as temperature being 300 K and pressure is 1 bar. We need to evaluate the ear angles, that is beta 1 and beta 2. The mean radius, the blade height, and the number of blades required. Let me solve the problem. The data are given at the mean radius, that is, I have been asked to perform pitch line analysis. What I have done, I have drawn here the inlet and exit velocity triangle of the rotor at the mean radius, where W represents the relative velocity, C absolute velocity, beta is the relative air angle, and alpha is the absolute air angle. Subscript 1 refers to the inlet and 2 to the exit. Thus, at the inlet, I have indicated that W1 plus U1 is equal to C1. U is the blade speed. Here, U1 is equal to U2 is equal to U. Beta 1 and alpha 1 are the angle that W1 and C1 makes with the z-axis. In the same way, I have projected the velocity triangle at the exit, that is W2 plus U2 is equal to C2. And I have indicated beta 2 and alpha 2. Note that being a compressor, the flow will be deflected. That means relative velocity would be deflected, and W2 will be less than W1, being the compressor. Relative flow will be decelerated, and also beta 2 will be less than beta 1. Further, I have indicated beta A, which is the vectorial mean angle, and I have indicated here lift and drag on the blade. Lift here is perpendicular to vectorial mean velocity. In this case, it's the relative velocity, and drag will act along the vectorial mean velocity. Now, after drawing the velocity triangle, I have stated here that stage temperature rise T03 minus T01 is equal to lambda u Cz divided by Cp into tan beta 1 minus tan beta 2. This relation I have already proved. Lambda is the work done factor, u is the blade speed, Cz axial velocity component. Thus, I know all the value, that is, it has been given that stage temperature rise is 22 equal to 0.95 into 200 into 157 divided by 1005 into tan beta 1 minus tan beta 2. Thus, I have got the relation tan beta 1 minus tan beta 2 is equal to 0.741. This equation I have denoted as equation number 1. Again, I know degree of reaction R is equal to phi into tan beta m, that is equal to Cz divided by twice u into tan beta 1 plus tan beta 2. I know the value of Cz, I know the value of u that I have represented here. Tan beta 1 plus tan beta 2 is equal to twice into 200 into 0.5, degree of reaction is 0.5 divided by 157. Thus, I got another relation, tan beta 1 plus tan beta 2 is equal to 1.27, and that equation is denoted as equation number 2. Let me pause here and just to tell you, the degree of reaction was given as 0.5. 0.5 degree of reaction means the velocity triangle at inlet and exit would be the mirror image of each other. So beta 1 would be equal to alpha 2 and beta 2 is equal to alpha 1. Thus, if I solve the equation number 1 and equation number 2, I'll get beta 1 and beta 2. Thus, solving this 2 equation, I have got beta 1 is equal to 45.16 degree, and that must be equal to alpha 2 as the degree of reaction is 0.5. Similarly, beta 2 is equal to 14.81 degree, that must be equal to alpha 1. So the first point that has been asked, beta 1 and beta 2, that I have calculated. Now the next point that has been asked is the mean radius. So I can write Rm is equal to u, that is tangential or the blade speed divided by twice by n, where n is the rotation of the blade, that is equal to 150 rps. So put the whole value 200 divided by twice pi into 150. If you do that, you will get Rm is equal to 0.212. Thus, I got mean radius as 0.212 meter. The third question was to evaluate the blade height. Now I have written here that the blade height can be evaluated from annulus area. Thus I have written here m dot is equal to mass flow rate through the compression is equal to rho 1a into Cz. Cz is the axial velocity, a is the annulus area, and rho 1 is the density of air at inlet. Now from velocity triangle I can get C1 is equal to Cz by divided by cos alpha 1. Thus alpha 1 equal to beta 1, that means equal to 14.81 degree. So C1 would be equal to 157 divided by cos 14.81 degree, it is equal to 162.4 meter per second. Now total temperature at T01 is equal to static temperature plus C1 square by twice Cp. From there, I can write T1, which is the static temperature, is equal to T01 total temperature minus C1 square divided by twice Cp. Now I have evaluated C1. I know total temperature at inlet is equal to 300. So put the whole values and you can get T1 static temperature is equal to 286.88 K. Now between the total condition and static condition, we can use isentropic relation. Thus I can write P1 divided by P01 is equal to T1 by T01 to the power gamma by gamma minus 1. Now I know the ratio of T1 by T01. So this right hand side is known. And since P01 is equal to 1 bar, you can evaluate from here the static pressure. Thus I got static pressure P1 is equal to 1 into 286.88 divided by 300 to the power 3.5. So if you do the calculation, you will get P1 is equal to 0.86 bar. Please check the calculation also. The rho 1 I got is equal to P1 divided by RT1. R is equal to 287. P1 just we have evaluated. So I have got rho 1 is equal to 1.045 kg per meter cube. So I have got P1 and rho 1 and T1 here. From continued equation, I can write E is equal to m dot divided by rho 1 into Cz. M dot is given as 25. Thus 25 divided by 1.045 into 157. That would be equal to 0.152 meters square. So this is the value of A. After evaluating A, that is annulus area, I can project the blade height H as A divided by twice pi into Rm. So H is equal to 0.152 divided by twice pi into 0.212. This would be equal to 0.114. Thus I have got blade height as 0.114 meter. Now the last part is remaining is the number of blades required. Now by definition we know aspect ratio is equal to pitch by chord. Pitch is equal to distance between the two consecutive blades. So pitch can be written here twice pi Rm divided by number of blade. So here number of blade I have denoted as n. So I have written as 0.8. 0.8 is the aspect ratio is given. So 0.8 is equal to twice pi into Rm divided by n into C. C is the chord of the blade. The value is given here. So I have written 2 pi into 0.212 divided by n into 0.037. Thus, I have got n is the number of blades as 45. Now I have got all the values asked. So answers are beta 1 is equal to 45.16 degree, beta 2 14.81 degree. Mean radius Rm is equal to 0.212 meter. Height of the blade H is equal to 0.114 meter. Number of blades required are 45. Let me solve another problem. The statement of the problem is the stages of a multi-stage axial compressor have the following data at the mean radius. The overall pressure ratio 5.0, degree of reaction 50%, mean blade speed 244 meter per second, axial velocity throughout the compressor is 160 meter per second. That means axial velocity is considered constant throughout the machines. Polytropic efficiency 88%. The relative outlet air angle for each stage is 30 degree. Ambient temperature 300 K. Ambient pressure 1 bar. Determine the number of stages required, the pressure ratio of the first and the last stage, the rotor inlet relative Mach number. Here also I have drawn the velocity triangle at the inlet and exit of the rotor at the mean radius before solving the problem. All the notations are the same as before. Now look, the degree of reaction is stated as 50%. Thus the velocity triangle would be symmetrical, and also alpha 1 would be equal to beta 2 and alpha 2 would be equal to beta 1. Furthermore, the stage stagnation temperature rise can be given as delta 0 is equal to T03 minus T01 equal to U into Cz divided by Cp into tan beta 1 minus tan beta 2, where beta 2 is given as 30 degree. Now from the velocity triangle I can write W theta 2. W theta is the tangential component of W2. So W theta 2 is equal to Cz into tan beta 2. The value of Cz is given as 160 and beta 2 is equal to 30 degree. So W theta 2 I have evaluated as 160 into tan 30 degree, that is equal to 92.38 meter per second. Now as the velocity triangle is symmetrical, so I can say C2 means this length, C2 must be equal to W1. Thus I have written here C2 is equal to W1 is equal to Cz squared plus C theta 2 squared. C theta 2 is the tangential component of C2. Now C theta 2 can be written as U minus W theta 2. So I have projected W1 as equal to Cz square plus U minus W theta 2 square to the power half. I have evaluated W theta 2. I know the value of U. I know the value of Cz. Thus W1 is equal to 160 square plus within bracket 244 minus 92.38 whole square to the power whole half. So if you do this calculation, you will get W1 as 220.4 meter per second. So I have got W1 here. Now Cz is known. So from W1 and CZ I can evaluate beta 1. Thus I have written cos beta 1 equal to CZ divided by W1. So I have got beta 1 as 43.45 degree. Therefore, after evaluating beta 1, I can assess stage temperature rise. Thus, I have calculated del T0, which is equal to stage stagnation temperature rise is equal to 244 into 160 divided by 1005 into tan beta 1 minus tan beta 2, thus tan 43.45 minus tan 30 degree. If you do the calculation, you will get del T0 as 14.37 K. Now we know overall pressure ratio as 5, thus we can evaluate overall temperature ratio from the relation as T02 divided by T01 is equal to P02 by P01 to the power gamma minus gamma divided by gamma into eta P. Eta P is being the polytropic efficiency. This relation I have proved. Thus, this should be equal to 5 to the power 0.4 divided by 1.4 into 0.88. 0.88 is the polytropic efficiency here. Thus, if I do this calculation, I'll get T02 by T01 is equal to 1.68. Now, this T02 I can write T01 into N into del T0, where N is the number of stages and del T0 is the temperature rise in a stage. So I have written here T01 plus N into del T0 divided by T01, that is equal to 1.68. Now I know the value of del T0, that is 14.37. I know the value of T01, that is 300. So I can evaluate N. When I have evaluated N I have got as 14.2. But number of stages cannot be a fraction, so I have taken the immediately higher whole number. So the number of stages would be 15. Since I have taken the number of stages is 15, thereby I'll have to reassess now del T0, that is stage temperature rise. So I have reassessed del T0 as T02 minus T01 divided by N. T02 is 504 minus 300 divided by 15. N is the number of stages. So 504 is equal to T02, which is 1.68 into 300. So del T0 now I have got as 13.6 K. So considering number of stages as 15, the stage temperature rise would be 13.6 K. I'll have to evaluate now the pressure ratio for the first and the last stage. Thereby the pressure ratio for the first stage can be stated as RS1 is equal to, within bracket, 1 plus del T0 into eta P divided by T01 to the power gamma by gamma minus 1. This relation I have proved, where del T0 is the temperature rise per stage, T01 is the total temperature inlet to the stage. Now del T0 is equal to 13.6. Eta P is the polytropic efficiency or small stage efficiency. Here it is given as 0.88. T01 as 300, and gamma by gamma minus 1 would be 3.5. Thus, if you do the calculation, you will get RS1, that is pressure ratio for the first stage, is equal to 1.147. Similarly, pressure ratio for the last stage would be evaluated. Now, look, this is not rise but the ratio. To do the pressure ratio for the last stage, I'll first have to assess the inlet total temperature to the last stage. Now I can write inlet total temperature to the last stage T01L is equal to T02 minus del T0, that is equal to 504 minus 13.6. It would be equal to 4.490.4 K. Thus, T01L, that is inlet total temperature to the last stage, is equal to 490.4 K. So pressure ratio here would be equal to, within bracket, 1 plus del T0 eta P divided by T01L to the power gamma by gamma minus 1. Thus is equal to 1 plus 13.6.8 divided by 490.4 to the power 3.5. If you evaluate this, you will get pressure ratio as 1.09. So pressure ratio for the first stage would be equal to 1.147, and that for the last stage would be 1.09. Furthermore, from velocity triangle, I can write C1 is equal to Cz divided by alpha 1. Now alpha 1 would be equal to beta 2 here is equal to 30 degree. Thus, I have calculated C1 as 160 divided by cos of 30 degree is equal to 184.75 meter per second. Furthermore, I can write T01 total temperature at inlet is equal to T1 static temperature plus C1 square divided by twice Cp. Thus, I have assessed the static temperature T1 as T01 minus C1 squared by twice Cp. So 300 minus 184.75 squared divided by 2 into 1005. And thus I have got T1 as 283.02 K. Hence the sonic speed A would be equal to root over gamma R into T1, that is root over 1.4 into 287 into 283.02. It would be equal to 337.2 meter per second. So what is the inlet relative Mach number? MR1 would be equal to W1 divided by A. W1 I have already assessed as 220.4. So 220.4 divided by 337.2. So I got Mach relative inlet Mach number MR1 as 0.653. Thus the answer are number of stages N is equal to 15, pressure ratio at the first stage as 1.147, and pressure ratio to the last stage is 1.09, relative inlet Mach number as 653.653. Hope these two problems will be helpful and you can solve the similar problem. However, I'll request you to check the calculations. Thank you for listening.